This is lesson 8.3, polar form of complex numbers. It's our second lesson on this. This is to build on what we've already talked about in lesson 1. So to recall that, I'm going to go pretty quick, and you're to use your guided notes and fill in. Pause the video as needed if I go too fast. So you're going to fill in the complex numbers in the form of a plus bi, where a is the real part and bi is the imaginary part. We're going to graph the complex numbers in this plane, but before you do that, you definitely need to label the axes in the plane, because that's what indicates that this is a complex plane. So we have our real axes and our imaginary axes. And so we're going to be plotting these 6 points where we're going to go in the horizontal direction, the real direction, and then in the vertical, the imaginary direction. The only two that are a little bit different are C and D, where we're going to add our complex numbers first before, or so add in for problem C and subtract in problem D before we graph the points. So here we go. We're going to graph point A, and there it is, point B. C, we add those two together, so 2 plus 3 is 5. Positive 3i and negative 2i is positive 1i, and then we graph point C. Then we're going to subtract 2 minus 3 and positive 3i minus negative 2i, which means to add, and then we have that graphed. And then for E, this just says go down 4 in the imaginary direction. And for F, we're going to go 2 in the real direction. You might think this is not a complex number, but it is. It's actually just saying 2 plus 0i. So there's the 2 points that are on those axes, E and F. The absolute value of any real number is the distance from 0. So the absolute value of a complex number is known as the modulus. This relates, as we had in our other lesson, to the radius when we're talking about a real point and we're finding out the distance from 0. We called that the radius when we were in real. But this is complex, and so we call that distance the modulus. We use the Pythagorean theorem, which is also the distance formula, to find that modulus, which is the same formula we used in real to find the radius, which is the absolute value of the complex number is the square root of the a squared and the b squared. Not bi, just the b, because you're counting how many reals and squaring them, how many imaginary, and squaring them and adding that together, taking the square root. We use the letter R for modulus, even though it does look like radius, it stands for modulus. So we're going to find the modulus for all 4 of these points. We take the square root of a squared plus b squared, simplify, we get the square root of 13. Remember, this is negative 6 plus 0i, so technically you'd say, oh, it's negative 6 squared plus 0 squared, which is going to give you the square root of 36, which is just 6, but we could have also just visioned this and said, oh, we're here at negative 6, and what's the distance to 0? Well, that distance is 6. And we didn't need to use the formula because we can visualize what that meant. For here, we've got negative 3 and 4. We get the square root of 25, which is 5. We also could have realized, 3, 4, 5, the Pythagorean triple, because remember, this is the Pythagorean theorem that we're using. 7i, very similar to number 2. We just go, we go 7 in the imaginary direction, and that distance is 7. Okay, we're going to write the polar form, and we're going to write the formula out. We had this on Friday, but we're going to redo it again. When you have it in its rectangular form, a plus bi, to write it in polar form, we need to find the modulus and the angle, and then we write it as the modulus times cosine theta plus I sine theta. If we had it in polar form and we wanted to find a plus bi, what we say is you just do it. You do r times cosine theta, and that will equal a. You do r times I sine theta, and that's going to give you your bi. For each of these problems, we're going to find the complex number in polar form, so we have to find our modulus. So for problem number 1, our modulus is a square root of 2. We need to find our angle, so we use the same formula we used for converting polar of real points. We use the arctan of b divided by a. and arctan of 1, remembering that this is in quadrant 1, because we would go over 1 and up 1. It's in quadrant 1. And when the tangent ratio is 1, we know the angle then would be pi over 4. So writing that in polar form, the modulus times cosine pi over 4 plus I sine pi over 4. We're going to do the same thing with problem number 2. Find the modulus. We get 2. We're going to find the angle. It's the arctan of negative root 3. And then we have to stop and think, which quadrant is this? Well, this is, you go negative in the real direction and positive in the imaginary. That's quadrant 2. So thinking about arctan in quadrant 2 when it's got a negative root 3, that's going to be 2 pi over 3, and we write in polar form. Problem number 3, we find our modulus is 8. Whoops, sorry, I went all the way through that, but 8. Then we do our arctan, remembering that we're in quadrant 3 because it's negative, negative. And this is going to be negative root 3 again, but that's going to be in quadrant 3, so the angle is 4 pi over 3. Excuse me, it's going to be positive root 3. And that's in quadrant 3, which means our angle is going to be 4 pi over 3, and there's the polar form. For problem number 4, we find the modulus. We use the arctan formula, knowing that we're in quadrant 1 since it's positive, positive. And therefore, we go, we don't know what arctan of 4 over 3 is without a calculator. So here's where we keep it in exact form, which means we keep it in arctan of 4 over 3. This just means theta, okay? So here it says the modulus cosine the theta, which is arctan of 4 over 3, and then plus I sine arctan of 4 over 3. And that's how we would answer the problem, because this is a no calculator question, okay? Let's talk about multiplication and division. We're going to write out the formulas. We did them, again, we did these on Friday, but I want you to have the formal notes for it. So when we multiply complex numbers, what we do is we multiply the modulus and we add the angles. When we divide complex numbers, we divide the modulus and then we subtract our angles. And whatever is in the numerator, that's what we always start with. So the numerator here, we had z sub 1, so we have r sub 1 in the numerator, and we start with theta sub 1. Remember that you're adding the angles for multiplication, you're subtracting the angles for division. So here's a problem to do. We've got our two complex numbers, z sub 1 and z sub 2. We multiply the modulus and we add the angles. We have to take a little sidetrack here to think about our fractions. Pi over 4 and pi over 3. Common denominator is 12. 3 pi over 12 plus 4 pi over 12 is 7 pi over 12. So there's the final answer. 10 times cosine 7 pi over 12 plus I sine 7 pi over 12. To do division, we said we divide our modulus, and then we subtract our angles. And once again, we need to do a little bit of fraction work there, subtracting those the 3 pi over 12 minus 4 pi over 12, which gives us negative pi over 12. So we know we're in quadrant 4, and there's our final answer. Now there's De Moivre's theorem, and De Moivre's theorem is how we can do powers of complex numbers. So we can raise them to some power. So here, first of all, it's saying when we have a complex number, r cos theta plus I sine theta, if we are going to talk about that complex number raised to any power, well, you're always just going to have the modulus raised to that same power. And then what you do is you're going to be multiplying the angle by whatever the n was, the number. So cosine n theta times plus I sine n theta. Let's do it with a problem here. So first of all, step number 1 is this is in a plus bi format. We need to first rewrite it into polar form to use De Moivre's. So we find our modulus, which was root 2 over 2. We find our theta, knowing we're in quadrant 1. When our a and b are equal, we know that's going to be pi over 4. So we have our polar form. That's step number 1. Now that we have our polar form of that complex number, we're going to raise it to the 10th power. So we're going to raise the modulus, root 2 over 2, to the 10th. And then we're going to multiply each of the angles, the pi over 4, times 10. Well, let's take a little sidetrack over here on what root 2 over 2 to the 10th power is. Well, root 2 to the 10th power, this is 2 to the 1/2 times to the 10th, which is 2 to the 5th. Because I just think of the root 2 as the 1/2 power, and then you multiply your two powers. 1/2 times 10 is 5. And the denominator is still 2 to the 10th. Now you have 2 to the 5th divided by 2 to the 10th. Like bases, you subtract their exponents, and you end up with, it would be 1 over 2 to the 5th, which is 1 over 32. And 10 times pi over 4, well, they both reduce by 2, and you're going to get 5 pi over 2. So this is the complex number in polar form when it's been raised to the 10th power. But it was given to us in a plus bi format, so we need to convert this back to a plus bi. How do we do it? Well, we just do it, meaning I take 1 over 32, and I'm going to multiply it by cosine of 5 pi over 2. Well, 5 pi over 2 is straight up. It's coterminal with pi over 2. And at pi over 2, cosine is 0, sine is 1. And so we end up with 1 over 32 times 0 plus 1i. And then distributing 1 over 32, we just get 1 over 32i. And that is the end of using this for demoivres. If we had been given our complex number in polar form, we could have stopped when it was in polar form. But because we were given the original complex number in the rectangular format, a plus bi format, we need to make sure our answer in the end is in that same a plus bi format. Okay, when you finish all your notes, then you should work on your homework until the end of the period. And I will see you tomorrow.